My name is Dan Friedman. This is Will Byrd. And we're going to try to entertain you today with some relatively amazing programs, and then maybe some really amazing programs. And we're going to start by doing a quick review of miniKanren, which is the language that Will and I have been working on for a while. And we have the standard operators, for those of you who are familiar, cond and run and fresh and equal, and from that we can write a little program. So let's just try something simple like run 1q equal q to 5. And sure enough, we return the value 5. Are you doing that, Will? Are you causing that? No? Okay.
I don't think so.
Let's try something a little more sophisticated. Let's put a cond in there. And just do something like run 1q, run 1q cond pren equal q to 5, q to 6. And we run this, and sure enough, we get both. We don't get both answers because we forgot to ask for 2 values. So let's try go for 5 values, I was thinking. But you can go for 2 if you want. And sure enough, we get our 2 answers because that's all there are. And finally, we might want to do something a little more sophisticated. So we're going to introduce a fresh. So we'll do a run 5q. And let's put a fresh right in front of that cond. We can put it anywhere, but we'll put it there. And we'll introduce a couple variables, x and y. And now we'll change that q to x, and the other q to x. And then
To
we
X?
will...
Both X?
Yeah, why not?
Okay.
And, but let's not be shy about y. Let's give x 5 and y 3, and x 6 and y 7.
No Y
Yeah.
on that one.
You know, all right, no y. That's a good idea. Sure.
All right.
Okay. I was going to do something about q, but I guess we can wait.
Yeah.
All right, let's wait. All right, so we get back the first answer. The first answer has the property that it succeeded, whatever that means. And so did the second answer. So now it's time to actually see what those are. And to do that, we associate a data structure with q. So we're going to end up with q equal to backquote comma x comma y. And now we see the answers are 5, 3, and 6. We don't know what y is in the second computation. So we end up with underscore dot 0, which says it's anything we want it to be. So that's pretty much the base of miniKanren. And of course, we haven't done anything with recursion yet. So before we do that, though, let's talk about the other operators that are floating around. We have added some. We haven't really subtracted any yet. So I guess it's the way things work. So we have this operator that says not equal. So we spell it equal/equal, but in print it's just the not equal sign through the equivalent sign. And so now we're saying that q cannot be 5 under any circumstances. And sure enough, it says it succeeded because we didn't do something that was wrong, but we're reminding you that, by golly, q, which is underscore 0, can't be 5. So but let's let it be 5 and see what happens. Let's do an equal q to 5. And sure enough, it fails. And sure enough, it fails. OK, so that's basically all there is to this equality. Of course, things can be much more complicated. You can have complicated expressions in there, but it doesn't matter. It's still going to basically give you the information that you wanted. So maybe this is not going to be equal to, let's try a backquote comma x.
What do you want?
Well, comma y. Comma y. Of course, it's going to fail. We're not finished yet.
Yeah.
Okay, and now we're going to say, oh, this is supposed to be not equal. Sorry.
Oh, not equal? Okay.
Not equal x comma y to q. And let's see what it does. Okay, now it's saying that, oh, this is an older version. So we have the underscore dot 0 is the answer. It succeeded again. But now suppose we do an equal x, we add an x to 5 and a y to 6 again.
Yeah. What do you think is going to happen, Dan?
I think I know.
I don't think you do. What is it going to do?
It will, well, Q is fresh, so it should succeed.
Yes, it should.
Yeah. Okay, but that's not what I wanted.
I know it isn't.
I wanted to now say something.
I think what you wanted to do was probably saying something
Yeah, something like that.
like
Yeah,
that, and then maybe put disequality constraints on x and y or
right.
something.
2 of those, and now we're in business.
And then you can, do like some unification. So here, we can unify x with 5 now, and of course that will fail. But if we have like the disequality constraint here, saying that they can't be 5 and 6 at this.
Tricky stuff. All right, we have 3 other relatively easy constraints. Symbolo, which we'll just do a real quick one on that one. It really is tricky. Equal/equal is easy when you say it and you understand what it's doing, but when you start thinking about all the relationships that it keeps track of, you're grateful, beyond grateful that it's there when you need it. Anyway, Symbolo says that Q has to be a symbol. So there it is. It says it's a symbol. But you can also do things like number, oh, yeah, of course. And you can also make them both. You can make a Q both a number and a symbol. Let's see what happens when you do that. It fails because nothing's a number and a symbol. Right? So those are 2 others. And then finally we have one of the great ones is called absento. Thank you. And absento takes usually a variable. All right. Usually a variable is the first argument. And Will is now taken over.
All right, now I can stop laughing. I'll start typing.
Okay.
So absento is basically like a tree constraint. It's saying that the first argument to absento can't appear anywhere in the second argument. So you can think of these as arbitrary terms. So actually both of those could be trees, or they could be variables or whatever. So it's saying that first term can't appear anywhere in the second term. Okay.
So we've added a new one. This is the first time anyone has ever seen this one from us. It's called eigen. So let's see what we can do with it. Let's just try eigen x and equal. And it fails. It fails because any existential that exists, which is your absolute Q, that has happened already, X can't be involved in it. That's not the thing. But it's like the difference between for all X that exist in Y and exists X for all Y. So it's strictly a kind of logical relationship in mathematics. Yeah, thank you very much. And that's what it comes down to. And since we're starting with this, we know that any variable in that chain cannot be involved. So let's try to build in a chain that I just do eigen x there. Let's start with x y there, and then we can say x y, and we'll be very happy. Succeeded. That's happened after the eigen. Now what happens?
So logically, this is saying that for all x, there exists some y such that x equals y. Okay, so that's different. If you switch the for all and the exists, that's not true, but this ordering is correct. So basically one of the principles is that you'll never see an eigen variable as a top level value, so it's never going to escape the run.
Let's find it to Q. Let's find y to Q. Y is not an eigenvariable, is it? Let's see what happens if you do that.
So sorry, what do you want to do?
The next thing in that thresh would be y gets Q.
Ah.
Any ideas? Well, it's going to fail because it's now become an eigen, basically, by virtue of the equal, and the eigen can't be associated with Q, so down it goes. Okay, so we're going to be using that a little later on today. Okay.
So the point of eigen is it lets you prove statements for all, for all values. So, it's sort of like a lexically scoped gensim. It's like I'm going to pick some value and I can't really tell anything about the properties of it, and because it's an arbitrary value that I can't really inspect, I can put it in a data structure, I can remove it from a data structure, I can compare it with itself, that's true. Comparing it with anything else is false. Basically, if I can prove something about a statement that includes that variable, that means it holds for all values instead of just some random variable.
Okay, so let's do our simple example. Define random row. So I could define random row.
Okay.
Lambda A-L on rho L is in the empty loop. We're removing the single value of the pure social factor. But that's not quite the factor, it removes all of them. It's a flat list. So each of Carvel to quote A.
To quote A?
We can test it real quickly. And you see the result here. Now, in order to rewrite this as a miniKanren program, all we do is add an O there, an out variable on the next line, change the con to con E to an equal L in the empty list. In this case, we want to have the empty list be out. Now the next line, we want to introduce places for car and footer, so that's fresh, A, E, and then when F is A is equal to flow, which that we have. I don't know what to
Oh, naughty Dan, why'd you call it A? You're messing me up. Okay. Yes. Yeah. Okay. So we can do a condia here, actually. So if A is equal to X, the thing we're looking for, then we have to recur on the cdr. Else.
And then we're going to cons the A, the A onto res, and shift them around a little bit, and I think that's it, right? Yeah, let's run it and see what happens.
Actually, I can go back to the old one. Yeah? Problem, Dan.
By the way, for those of you who may have seen the recent consumer version of it, at this point we have to do the surprise. The surprise is us. So finally we realized that what we have been doing for a long time is we use quality constraints. And so when we know that we have to say that. Okay, we can't be X. And then we pop in the line, and then we go, and now we get okay, so now we're ready to look at a short string program that does a finite standard time. Now, for those of you who have this course, finite standard time, just get the same thing. That's the category. But this finite standard time is sort of the first or the simplest of the Chomsky hierarchy, right? And right after that, we have CA, and and the difference between the finite standard time and CA is that stack is so we get this. Okay, so and here is a non-deterministic finite standard set. But we're going to first look at the deterministic one.
No, we were first going to look at this one. Well, okay, so this is, when you're designing a state machine. Yes. I took all these great photos in the hotel lobby, which apparently has like a green light. So here's the overpriced but excellent book by Sipser. This is my favorite book on formal languages. It's like ridiculously expensive, but it's very, very good. Yeah, so here's an example. Non-deterministic finite automaton. It's non-deterministic. Okay, so first of all, if you're not familiar with finite automaton, here's an automaton that has 3 states, 1, 2, and 3. The top one is an accepting state. It has this extra circle around it. And then we have, we can also see the first one, state 1 is the starting state. It has an arrow coming in. And we have labeled transitions. So here we have a string containing letters in the alphabet, A, B. Well, I haven't gotten to that, Dan. Okay, so these transitions are telling you how to consume a letter at the beginning of the string, and then it brings you to a new state perhaps, or in this case, back to the same state. And if you end up consuming the entire string, and you're in one of these states, well, if you're in a state that has a circle around it, then you've accepted the string in the language, otherwise you reject it. This epsilon thing is a transition, a non-deterministic transition that you can perform without consuming any of the string. So if you're in state 1 and you have a string, you can either, if the string begins with a B, consume that B and move to state 2, or you can immediately jump to state 3 without consuming any of the string. Okay, so this epsilon transition, that's one of the hallmarks of a non-deterministic finite automata. The other thing to notice here is that there are 2 ways to get out of state 2. So we can either consume an A and stay in state 2, or we can consume an A or a B and go to state 3. However, importantly, if we have a string that starts with an A, we can either stay in state 2 and consume it, or consume it and go to state 3. So we have a non-deterministic choice once again. And the traditional way to implement this sort of system is to turn the non-deterministic finite automaton into a deterministic finite automaton. There's algorithms for that. Sipser talks about that, for example. And what you get for that particular DFA, or sorry, NFA, is this thing. So we went from 3 states to 8 states. And for the 8 states, we can see now we have 4 accepting states, and it's just a much more complicated figure. But we can then do some more translations, and we can minimize that and get this DFA that has 6 states instead of 8. Okay, but this is still more complicated. The nice thing is now we don't have any epsilon transitions. We only have one transition coming out of each state. Every state has should have have a transition out of it for each letter in the alphabet. So it simplifies the implementation, but we have to go through several steps. So we have to take our non-deterministic finite automaton, make it deterministic, probably want to minimize it because the states can explode, and then implement this thing, which is in some ways more complicated, and we have to do all the work of translating. So it'd be nice if we could just implement this directly, right, as a non-deterministic finite automaton. And as designers of systems, if we're trying to create a state machine, it's often nicer to create a design using a non-deterministic finite automaton, and then we can massage it.
Okay, so let's go to the theme programmer that is very simple. And what's important here is that all we're doing is encoding each state as a function. And you may notice that all the calls to the state applied to arguments are what's called in tail position. So let's see what happens if we were to trace a little program. This is just a final program, nothing fancy. So we can do trace lambda on each of those.
Okay, so
Okay, now we can run this. And you see that we're not getting deeper into the search. So it turns out that it's actually, and I know can't do this well, actually generates the code. Use one in the program, but still stay to determine. Okay, so now we're going to look at the first. You want to go to the big one first or the small?
let's go to the big one.
This big, okay. So we've got the 6th state right here. And notice that the code here has the tail call for the go-tos. That hasn't changed. And notice as well that we are writing it in miniKanren. So we've got on the in multiple places. There's a piece here where we're saying what to do if we see an A and what to do if we see a B. And the first one of those equals is just taking the string apart and constructing the string into a first element and for the remaining elements. Most of the time we look at the first and then the recursions on the remaining. So all of these states basically look the same, except if you look closely, you can see on those red, some of those are the accept states and some of them are the reject states. So it's just kind of a minor difference. And one other reminder is always start with the available.
So just to clarify Dan's point, accepting states have a clause that say if the string is empty, we're going to succeed without any further work. Okay, so if you want to have a reject state, it's easy. You just don't have a transition in that case. So if you end up with the empty string in a reject state, you just fail. You don't produce any answers. And then otherwise, this is just tearing apart the pairs and doing state transitions by doing these tail recursive function calls. Okay.
So if you now do the transformation to minimize, this is no longer using minimize. We can now just take the NFA
Well, it turns out that they're equivalent, and we've got some tests that show that. Yeah, but the important point here is that this is the non-deterministic version, and we didn't have to make any changes, basically. So if we, let's see if we can find our picture here, hopefully we can see that there are similarities here. So see. Okay, so let's see here. There are 3 states. So this is how to write your own non-deterministic finite automaton. So there are 3 states. Each state is represented as a lambda, basically as a tail recursive procedure. These are mutually recursive. So this is state 1, this is state 2, this is state 3 at the bottom. And state 1 is the starting state. We can see that we're starting out with Q0 being returned, so that's the starting state. And in the first state, we can do 2 transitions. We can consume a B and go to state 2, or we can do a non-deterministic epsilon transition and just not consume anything and jump immediately to state 3. So the way this is written is, first of all, since this is an accepting state, it's got a circle around it, we have this clause to see if it's accepting. And of course, this is very, very regular code. We could easily write a macro that generates this stuff, right? And Sriram Krishnamurthy has a paper on doing exactly that for Scheme, but you could do it just as easily for miniKanren. So if you have the empty string, then we're going to accept in this state. If you are otherwise, we can immediately jump to state 3 without consuming any of the string. So this is the non-deterministic, or this is just the epsilon transition. And then finally, we can actually, if we have a non-empty string, we can tear it apart and check to see if the first thing in the string is the symbol B. And if so, then we can immediately jump to state 2 with the rest of the string. So those are the types of transitions we have. Nope. Okay, so yeah, so this is called N40 because this is the 4th non-deterministic automata in Sipser's book. So we can do like a run 1Q, and let's pull N40 and give it a string. And let's give it the string. So these are A's and B's. Does it accept A, B, B? Does it accept ABBA? And the answer is it does. Okay, cool. And we can let it play a little bit on its own as well. So we can just give it a variable there. And now a set of accepting strings is generating strings. So it accepts the empty string. So what are 10 more strings? Okay, so it gives us back different strings here that are all accepted. So we've turned our acceptor into a generator, and we didn't have to go through the process of making it deterministic. And this is a trick that's been known in Prolog for a long time, that you can keep your finite automata non-deterministic and then use the non-determinism in your underlying system to get that ability without having to do any of these translations or a state explosion. Okay, and then let's see. So the tests to show that these are equivalent, I mean, this isn't a proof, but this is some evidence that, that the 2 systems are equivalent, is that we have the non-deterministic version N40, and then we have a deterministic version, which is DO. And this little test, what it does is it calls miniKanren with a run 200. So we're generating 200 strings that are accepted by N40. And that's on our list ants. And now we're just looping through these answers. For each of those answers, what we're going to try to do is see if DO will eventually produce that answer. So we'll let DO just produce its own answers, generate a bunch of answers, and check to see if any of the answers match the answer we're looking for. So sort of a generate and test idiom lets us try to check to make sure that those are equivalent. Okay. And then there's kind of one more thing that we could show with this. And that's one thing you can do that's kind of interesting is you can add an accept or reject flag, basically. So instead of just succeeding or failing, you'll actually get back accept or reject if the automata consumes the entire string and ends up on some state. If it fails because there's no matching transition, then you'll just get back, you won't get back that answer at all. But the cool thing with this is that we can feed in, I don't know, this isn't the PDA. But I can show you, for example, in this one. So this is just a very simple automata. I can show you that's the state machine for this one. So the cool thing is, I can say, give me 10 strings that result in accept. But I can also say, give me some strings that are rejected, right? And it'll give me rejected strings. And we actually showed this in Norway when we were at FlatMap with a different approach using sort of an interpreter-based approach. But that's kind of cool stuff. Yeah. Okay. So the thing about the PDA is now we've added a stack to a non-deterministic machine. So we still have the notion of epsilon transitions once we get to a push-down automata. So we can look at
Yep.
Here is our transition
This is actually
diagram.
fairly straightforward. The first one, of course, is it's an epsilon transition, but it also says that if the top of the stack, so to speak, is an epsilon, and you do get to pop it, but of course that's doing nothing, then you replace it by a dollar sign. It's a very clean model. Here's a better example. Here's one where we see a 1 on a transition. We know there's a 0 on the top of the stack, and we don't do anything with the stack.
So we
after we've
consume the
popped
0
it.
in this case, and we don't push anything on the stack.
Right.
So, yeah, so there are two things here. So our states are the same. We have 4 states here. We've got Q1 and Q4 accepting states. Start with Q1, that's why it's got the arrow. And then we have an epsilon transition, means we don't have to consume anything from the string. And then to the right of this, these are the stack manipulations. And epsilon on the left means we don't care what's on the stack. We're not popping anything. And then whatever's on the right, if that's an epsilon, it means we're not adding anything. But in this case, we're pushing on a dollar sign. And in this case here, we're popping off what had better be a 0, otherwise.
Does anyone recognize what this machine does? Yeah.
Yes.
Exactly. Have to be the same length. So let's see what happens if we run it. And sure enough, if you look at those closely, the
Oh, no. So let's
yeah, it's a better thing to do.
Okay, so here are 10 strings that are produced by this
And
machine.
they all look like the right ones.
Yeah. So once again, we use our trick of the epsilon transitions mean that you're not actually looking at the string in any way. So you don't have any string manipulations. Accepting states we're still representing as having a special Condi clause saying that the string can be empty. And otherwise, we're doing, the only other thing that's new are these stack manipulations. So in this case, this epsilon transition, we're pushing the dollar sign onto the stack. We've got the old stack here, and we're pushing dollar sign onto it. We're just representing the stack as a list. And let's see, in this case, we're expecting to see a dollar sign on the top of the stack, and then we're transitioning into Q4 without changing the string. So this is an epsilon transition, and we're pushing in the rest of the stack.
Okay, so Does this cover all the things you want to talk about with respect to this machine?
Yeah, I think so. We could.
Okay.
We'll have a couple other things in the posted code, but
Yeah,
I want to get to like the good stuff.
I do too.
Okay.
All right, so it's Quine time. So we're going to do some Quines for you, but maybe a little variety this time. So,
1 second. Okay.
okay, so are you ready to run a Quine?
Yeah.
For those of you who have had a chance to see our talk at Strange Loop last year, we spent a fair amount of time on Quine, so we're not going to do that today, but we have one really nice one coming up. Oh, so here's the entire Quine system, and we're not going to explain that again. So let's just, but it does have things like car and coder and cons and quote, which you don't normally get in our normal 3-line interpreters. So here's our running of this, and here we go. Let's get a Quine. Here we go. What? Well, yes. True evaluates to true. So we're all set. Indeed. So let's try 2 then. Oh, and false evaluates to false. All right, one more shot. Oh, and there it is, our first Quine. And of course, we can run as many as you want and stuff like that. But now we're done with Quines. Yes?
Okay.
So do you have a second?
I don't know if I have a second. I've got a few milliseconds.
3 milliseconds. All right. Do you have like 20 milliseconds?
I've got 20 milliseconds.
Okay. So I would like for you to show everyone using the same program something, let's just say a little different. So oh, look at this. Matt Might has a blog post where he wants to generate 99 ways to generate programs that say, I love you. Okay, that seems like a nice thing to do. So, so Will saw that and said, boy, that's easy.
Well,
And-
technically, it was his grad student, PD.
I'm sorry?
His
Well,
grad
yeah,
student, PD,
right.
said, hey, you should try this.
In miniKanren. So here he goes. And the result is, don't forget to take the, oh, you forgot to take the length, the time. And 15 milliseconds later, we have 99 bottles of beer on the wall. I don't know.
It's a very clever shell script.
Okay, now we're really going to change directions a lot.
You know, so here's the problem with miniKanren. Like after we showed Quines, which we have to keep thanking Stuart Holloway for, but after we showed Quines, it was really hard to impress people with miniKanren after that. So, you know, PD said, okay, can you do this? It's like, yeah, I did it in 15 milliseconds. Like, what else do you want me to do? And no one was impressed, so I generated 1 million Quines.
No, 1 million I love you. Like,
A million,
I love yous.
sorry, not 1 million Quines, 1 million I love you programs, right? And I sent an email, I was like, hey, I generated 1 million I love you programs, and like, no one even responded. I was like, okay.
What can you do? What can you do?
What are you gonna do?
Okay, so we're going to change the flow a whole lot now because we may be talking about things that you're not familiar with. We're going to talk about something called combinatory logic. And just a quick history of combinatory logic and lambda calculus. In 1920, Moses Schoenfinkel gave a talk. In 1924, his paper got published, and if those of you want to read it, it's in Hagenor, a book called From Frege to Gödel. It's a collection of papers, fabulous collection of papers. And then around 1928 or so, Curry came into the picture, and he developed something called combinatory logic. And we're not going to do all the logic stuff. We're just going to do the computing aspects of it. And at this point, we should be looking at a page full of combinators, perhaps.
Okay.
And Ray Smolian wrote a book called To Mock a Mockingbird, which is for children, for young people. And turns out Schoenfinkel is a bird, and so he did everything in terms of birds as a sort of thank you to him. And this book, which was actually done by a PhD student who graduated in the philosophy department, but Katalin Bimbo, a great book on combinatorial logic. Okay, so can we see the list of combinators?
Those are two good books on combinatorial logic.
Yeah, those are our two standards. Okay, so these are very simple rules to read if you know how to read them. Okay, and that doesn't necessarily follow. Okay, so for example, let's just look at this S combinator on the right over here. That really says S applied to X. And then that returns a function. And then we take that function and we apply it to, well, it's Y. Y. Okay, and that returns a function. And then we apply that function. Actually, that's what it means, but this is what it does. That's what it means. This is what it does. It produces X, Z as one application, which has to return a function, and then Y, Z, which is just the second thing. And it basically, you're shifting around pieces of information. That's all you're doing when you're writing combinators. Okay? You just move them here, move them there, and so on. So look at W, for example. W says if I come in with two values, I just copy one of them and leave the others alone. So it's kind of like an equality, which of course is our bread and butter. Okay, so let's just go right to some of the examples because we are running short. Will?
Okay. Let's go to the real. So how much time do we have? Net minus 3 minutes? Okay.
Yeah.
All right. Since you've waited this long and been good, we had some problems.
Okay, so we have this really neat program. Go for it, Will. Go for it.
Here's kind of like the whole point of this talk. Everything else kind of
By the
doesn't
way,
matter.
these things are equivalent to Turing Machines, so we have covered what we promised to cover. But if you want to see Turing Machines in the same style, but without Condi, but it's still trivial, in Scheme and the Art of Programming, I did that some time ago. And if you can find the book, then you can see how we did it. Or you can send me an email and I'll Xerox a couple pages for you. Or photo with them with my camera, whatever's convenient.
If you're watching at home, you can skip to this part of the video. But it's too late. Sorry.
So all this, by the way, is just by reading the book and writing equations and thinking really hard, which Will did.
Enough talking. Look, here's Contracto. Contracto has definitions for three combinators, I, K, and S. So look at I, for example. I is just the identity function. You apply I to some argument, and you get the argument back. This is just shorthand for that pattern matching. And then we have K and S. So I, K, and S together, those three combinators, that's Turing complete. You can express any computable function with those three. Actually, you only need S and K. Okay. All right. So we have a very simple miniKanren for this program for this. And in fact, I will show you how short it is if this is the racket code for the entire system. Okay. So this is the reductions for the combinators. This is to perform a single reduction anywhere in a term. If you have an application, you might have to look inside the terms to find a single reduction. And this is the reflexive transitive closure of the single reduction. Okay? So sort of like you can imagine a little Lisp interpreter, as Alan Kay says, the Maxwell's equations of computer science. This is an alternate take on that. And this is the relational version of it, just like we had the relational version of the lambda calculus interpreter.
And there's our friend Eigen.
Here's our friend Eigen. Here's a query. What does this do? Run one Y. Eigen X. So this is saying that there exists some combinator called y, such that for all x, y of x equals x of y of x. Okay?
This is the Y combinator.
All right.
And we're about to generate it.
So here's the version that's not using the pattern matching. It's just using the language we showed you. So it's a little bit longer, but it's simpler to understand maybe. And now that we've loaded it, so this arrow WO thing, that is doing a single, sorry, that's the transitive closure there. So that's the relation we want. And oops. So what I'm going to do is run one. Y. Okay. Eigen x. And we want to y of x goes to x of y of x. Okay. Now this can take a few minutes to generate. So I'm going to give it a little hint. I can do it without the hint, but just for time, I'm going to give it a little hint. And the hint I'm going to give is that this combinator, that there exists a version of the Y combinator that basically is another combinator applied to itself. So here's just a little hint, it's a little guess. I actually didn't know this existed, but I took a guess and it was right. So I'm going to say Y actually looks like this. It's some combinator question mark applied to itself, and the rest of it is just a definition, okay? So let's see if this comes back. Let's see. Anyone got a stopwatch? Probably should have done optimized level 2. The fun part of this is if I made a typo, it will never come back. Yay!
There it is.
Okay. Now, hold on. Okay. So we got our Y combinator. We got our SKI combinator, right? That's cool. But the problem is, this isn't scheme code. This isn't closure code. This isn't racket code. We can't run this thing, right? So what we're going to do is we're going to call a little helper here, which is Ada.
Now, that is a...
maybe not the best.
Ada is an operator in lambda calculus that allows you to take something that is about to go into an infinite loop and close it up so that it can't go into an infinite loop right now. And that's when you end up with what's called the Z combinator, because scheme is a call-by-value language, and this is not designed in the call-by-value language. So
How do you like my beautiful Y combinator?
Well, it got a little larger, but it's still going to work. So let's see what happens now.
Okay.
Now you're in scheme, right?
I am in scheme.
So you could define Y as the value of this expression?
I could.
Then do it.
Okay. Define Y to be that thing. Okay. Whoops.
Okay, and now that you have
Y
it.
is that.
Okay.
All
And
right.
now you can say.
And now I've got
Y.
one more thing. Hold on. Okay. Here we go. Yeah. There we go. Yay. Okay.
Y.
Okay. So this is our friend factorial, but
Why don't you do what I always do? Change the F's to factorial so at least it looks sort of like it.
fine.
Both F's.
Okay.
Kind of looks like it, except there's this free variable called lambda in the part that looks like factorial, and you got to do something about it. So whenever you have a free variable you don't like, you just wrap a lambda around it, and everybody's happy. And do we get 120? We do. And so that really ends our talk. I wish we had more time. We certainly have more material.